All right.
Okay.
I'll hit it.
Great.
And we're live. All right. Welcome, everyone. I don't know if we have people already. I think we don't yet. But as you join, oh, we do. It says concurrent viewers 10. Okay. So as we get started, tell us in the chat, where are you joining us from? And I'll introduce myself in a little bit, but just to start, tell us where are you joining us from, and what you do, what is your favorite Dask thing? Have you ever used Dask? And yeah, and then let's get started. All right, see, Gus is here. Gus Adler, hello, Coiled. I'll talk a little bit about myself while we get started before we kick in with the material. So, hi everyone, my name is Nati Clementi. I'm a software engineer at Coiled. I'm on the open source team, and my day-to-day is working with Dask. And hence today we're doing a Dask live tutorial to get you started and then hopefully enjoy what we like about Dask. If you haven't checked on the material here, I'm going to post in the chat a link. If you are set up, if you're set up to work locally, you should have followed the instructions that are on that link. Right now, it might take you a little bit. There should be a binder button. So I'm going to show you quickly. I'm sharing my screen. If you go all the way down in the README, you will see the binder button. So click on there, and then you should be able to see the material. And we start in like 2-3 minutes. Just so you know, in the chat, we have Sarah and Ian. They're teammates at Coiled. They will also work for Coiled on the open source team. And every time that you have a question, they're going to be asking, they're going to be answering your questions in the chat, as I might not be able to see those questions. So feel free to ask any questions you have on the chat, and hopefully, and I'm pretty sure they will, Sarah and Ian will be able to answer those questions. If you have any questions about Coil in particular, towards the end of the tutorial, we're gonna have a sneak peek into Coil, and then I will let you know how you can try it for free, and hopefully you get to use Coil too. All right, so we'll start in 1-2 minutes. Currently, you should be able to be set up. So tell us if you're having any problems getting set up. You should be able to see everything on Binder, and you should see something like what I'm seeing in this in the screen right now. You will be able to hit on where the notebook's at. So I'm going to actually get us there first. And if everyone is okay, if everyone gives me a go, I can start right now. I will open the first notebook, which give us a kind of quick overview on what is Dask, and maybe we can answer some of the questions that you might have on what is Dask for, what is it good for, when you should use it, and so on and so forth. So one quick check, is the font, especially the small font that shows in here, big enough for you all? Comment in the chat and tell us yes, no, should I make it bigger? So we know if we need to make this big. All right, we have someone from Greece, someone from Costa Rica. That's very nice. Luis Gonzalez from Costa Rica, if you need to ask questions in Spanish, post it in there. I also speak Spanish, so not a problem. But make it bigger. All right. I guess small, but using binder as well. Good. All right. Hopefully that size is better. Chai, let me know if that's good. Happy to always make it even bigger. All right. We are at 5:05, so thanks everyone for being here. We're gonna get it started, and hopefully we'll fill this in about an hour and a half at most. Again, Sarah and Ian are in the chat to answer questions, so feel free to ask in the chat, and they'll take care of you as I go. Right. So if you join this tutorial, probably you are using Dask or and want to learn some other things, or you are new to Dask and you want to know what is it for, when do you use it, and how can make your life easier. So if you ever heard of Dask, you might have some sort of these questions. And if you have never heard of Dask, well, maybe you are in the right place, and we're going to answer some of these questions. So before we just dip into an overview, there is great material about documentation on Dask. You have all the links in the material we provided you. If you want to contribute to the project, you can go to GitHub. If you want to engage with the community, there is a Slack channel, as well as if you have questions of usage, especially after this tutorial, we highly recommend you to go to the Discord group that is listed in here. So on a nutshell, like, what is Dask? So Dask is a flexible library for parallel computing in Python. And it follows the syntax of the PyData ecosystem. So that's what makes it nice, because if you're familiarized with NumPy, pandas, and Scikit-Learn, then Dask is like their faster cousin. So things that in pandas, like reading a CSV file, looks like this code on the left, where we have imports pandas as PD, and then we don't read CSV. We give a CSV file, and then we perform a group by operation. In Dask will look very similar. You might notice on the right that we have here some asterisks. We will go over what this means, but like as a quick overview, what we're doing here is like reading multiple CSV files at the same time. And each of those CSV files will be what it's a partition, and it will look like a pandas data frame. Now, since pandas and Dask and NumPy, they're all family, Dask allows you to scale your already existing workflows with a small amount of changes. And in most cases, it's with a small amount of changes. In other cases, we need to do a little bit more work. But in general, like, Dask will enable you to accelerate and have more performant operations in your existing code. So how does that work? Dask can work like in your laptop, but it also scales out to clusters. And it could be in the cloud, it can be on big machines and that are physical machines. But in general, the main concept or the main idea behind Dask is that we have multiple collections. So Dask array is similar to NumPy, Dask DataFrames, similar to pandas, and so on and so forth. And we will create what is a task graph. And then that task graph will be passed to the scheduler, which will execute this task graph and then send it to the workers to perform the computations. And we have different types of schedulers, single machines, and distributed schedulers. We will go over what this means, but so far in your head now, the idea is we have certain operations, we create a task graph, and then the scheduler will send it to the workers, they will do the work, and we will get our computations. So in those sentences, I said a lot of words, and there is a lot of jargon behind what is distributed computing, and especially in Dasks. So when I talk about client, scheduler, and workers, what do I mean? When I talk about the client, is the user facing entry point for cluster users. So in other words, the client lives where your code lives. So in this case, in my case, I'm running this on my laptop, and I have here my Jupyter notebook, so my client lives on my laptop. When we're using cluster, this is not necessarily the same. The client might live on my laptop, but then the scheduler and workers will live somewhere else. So what is the scheduler? Scheduler is the task managers and is the ones that is in charge of sending the task to the workers. And as you might have guessed up to this point, the workers are the ones that compute the task. So notice that like the scheduler and workers are on the same network. They could live on your laptop, but they could be separate, as I mentioned before. So in general, this is like a look on how things get moved around with that. So we start with the client, then with the scheduler, and the scheduler send things to the workers to do the work. So there are usually multiple questions. If you've been using pandas or Scikit-Learn, and then you might be aware of Spark and PySpark and Dask and things like that. And it's like, when do we use Dask? We're not going to get into comparisons between Dask and Spark. Like, there are plenty of materials and you can read about that. So if that is one question that you might have, we can link you to multiple blog posts that they're written about how do they compare, when do you use one or the other, or what is good one or the other. But in general, like if you have all your workflow in pandas and the Python ecosystem, transitioning to Dask should be more or less straightforward and familiar. So when do we use Dask? There are a couple of questions that you can ask yourself to know when you can use Dask. And before trying to use it, you might want to determine whether it's suitable or not. Not necessarily always Dask will be the answer to your problems. So a simple question that we always ask is, does your data fit in memory? If your data fits in memory, meaning fits in your RAM and your data is like small size, 2 GB, 4 GB or so, if it fits in memory, then you should stay with pandas and NumPy. They're great, they're very optimized, and Dask might not be able to help you. So that means that you don't have a problem. Now, if your computations take forever and they're super long, then this might be a case where Dask can help you. If not, awesome, you have even less of a problem. Now, another question that we usually ask, or when people ask us if they should use Dask, is, do you have embarrassingly parallelizable code? And some people do not know what Dask means. So for that, there are a couple of links that shows you what this means, but basically is that we have one set of actions that we repeat over and over and over time for different parameters, like for example, a grid search. In that case, Dask will be able to help you. Now, in terms of on a graph or on a plot, how do we know when to use it or not? This is a good idea on when Dask is a good fit or could be a good fit and when it's not. So if you are on the left bottom corner where it says fits in RAM over here, you don't need to use Dask. Staying in the pandas, Scikit-Learn, NumPy world will be much easier, simpler for you, and this will do the job. If you are in any other place, if you have a problem that is compute bound, or if it's memory bound, meaning that you're running out of memory, or you have longer computations, Dask is fair game, and we will see some cases where we're using this. So just a couple of disclaimers, not always things will work easily. Sometimes you need to do more work. There are extended tutorials and trainings that can be very useful if you want to get deeper into how to use Dask. But for now, if you're interested in getting started and then you don't know if, am I doing the right thing? Am I doing the wrong thing? How can I fix this? There is multiple sources of best practices that I've linked into this material that you can check and see how to approach this kind of problems. And now let's get a little bit into more code. I've set certain extra materials for bigger tutorials and other talks that you can check, but more or less, why using Dask? if you're interested in knowing why Dask might be a good option for you, you can always check documentation. There is a written documentation on why Dask. But in general, what I would say is, do you have all your existing workflow in Python? Do you already use pandas, NumPy, Scikit-Learn, and all the PyData ecosystem, and you want to make your things run faster, or if things don't fit in memory, then Dask is the right answer. So let's get into some code and see how we can use Dask, or how can we get things out of it. So we're going to move to now notebook 1. So for you that are following on Binder, switch to the notebook number 1. So I'm gonna close this one. Seems that we need a little bit bigger font. So sorry, I just missed that. Hopefully this will do it. This might be even too big. I apologize. I cannot get it bigger, but I'll recommend you to maybe zoom in a little bit, or follow the material along in Binder. That might help you to see this, this material directly. Okay, so one of the first things that you might wonder is, I already have existing code. The code is working. What is the smallest amount of changes I can do to test if these things will run faster? So I will introduce you right now. One of the Dask collections is called Dask Delayed, and it's an interface that can be used to parallelize Python code and custom algorithms. So if you already have those that kind of code, and then you want to just see if it will run faster and if it will run in parallel, this could be a way of checking it out. So a first step to determine if we can use Dask Delay is to identify if there is some level of parallelism in your code. If your code cannot be run in parallel, then Dask Delay won't be able to do much. But sometimes you can modify your code a little bit to make it run in parallel. So let's see a small example where this is obvious. So here we have two simple functions where we are simulating to do some work by putting a sleep of 1 second, but we have two functions. A function inc that increments x, the argument, by 1, and then a function add, which will add x and y, and we'll also have this sleep of 1 second to simulate that we are doing some work. So far, nothing has run in parallel. Things are simple. We are in Python land. And let's see how long it takes to perform these computations, like on a serial code as regular. So if we check on this, yeah, it took like 3 seconds. So if we see where those 3 seconds come from, you see that inc, this is about 1 second. A second call to inc will be another one. And then when we sum on z, we sum x and y, we have another 3rd second. And the extra remaining time is everything that is behind the hood computing. Now, if you see this computation, this is serial computation, we are computing x first, y second, and then adding them. Now, x and y could be run in parallel. There is no need, they don't depend on each other. So this could look something like this task graph that we have here. We have two inc calls. They give an output. So two inc calls are these circles. We get two outputs that we actually pass them to add, and then add performs the result. So how can we use Dask to perform the computation, something that resembles this task graph that we have here? So let's use Dask Delay. So we import delay from Dask. Then we're going to time it here. So the way that delay works is Dask Delay is the decorator that will transform our inc and add functions into parallel versions of these functions. So the way that we do it is we decorate inc with delayed, and then we give the argument in case this will be 1. So this will be like what we did before with x. We do the same with B, so we will get delay ink 2, and then last step to get C and get the result, we will see, we'll do delayed of add and then pass A and B. So when we run this, what happened? We have only 2 milliseconds. But wait, I mean, this is way too fast. Well, what happened here is nothing has been computed yet. And that's why this only is taking like milliseconds. So what this is doing is generating a delay object. So let's inspect it. As you see here, if you print C, there is no results. I'm not seeing the result of adding A and B. So how can we visualize this? So we call visualize. And you can see that now this is a task graph similar to the one that we showed you before, where you're having the 2 ink calls, getting an output, passing them to add, and then getting the final result. So now how do we get the result? We need to actually call compute. So let's time this and see how long it takes. All right, so we got the result, there is 5, and then we see that this is taking 2 seconds. And the reason why it's taking 2 seconds is because now these 2 calls of ink are being run in parallel. So they both are run in 1 second. And then the second second, sorry, I'm being a little redundant, comes from the add call, where we're passing them to add. So if you are in Binder, and I apologize for this, but we have a workaround on you, you might have not seen that the wall time went from 3 seconds to 2 seconds. Now, this is because on Binder, everything, we only have limited resources. So if you're running this notebook, you won't see the speed up probably. And it's because we have one instance with 1 core with no threads. So you can't see parallelism in there. There is a fix to do that and to see it. We ask you to, if you can copy this code, this piece of code on a cell, and then try to run it again, you will see that a speed up of thing. I will go over what this configurations means later on, but for now, so you can see the speed up, try this out. So let's see how can we use delay to parallelize a for loop. Probably in your workflow on a day-to-day, you will have some sort of for loop computations. So let's see how we will make these computations faster with a simple example. So we create some data here. It's like a list of integers from 1 to 8, 0 to 7 actually. And then if we run this with no parallelization, this should take approximately 8 seconds, right? Because we're calling ink 8 times. So, and appending the results to a list. So we'll just run this. And for now, you can start thinking on how could we make this to run in parallel? And there's a little hint in here, just found a typo there, where you can do something in this line and then something in this line to make things run in parallel. So we print this is 36, and I'm going to give you the solution now. But basically, what we're trying to do is decorating our ink function, as we did before in the other example, but within the for loop, and we are delaying here to sum. So basically, we're sort of waiting for all these results there, and then we need this to take the parallel versions that were coming before, right? So if we do this and run this, let's see how long it takes. Remember that so far, we've only created the delay object. So you can see it with the visualize. So all these ink calls, the 8, if you count over here, you should have 8, will happen in parallel, create the result, pass it to some that is like over there waiting for these results, and then boom, we get the final result. So we call compute on this. You see that it takes 1 second. Now, that's 1 second is because all these computations, the in computations, run in parallel. Now you might wonder, well, how can you perform 8 of this in parallel? Well, that will depend on your machine, how many cores your machine has, and there's a way of expecting how many cores you have. If you do import OS and see the CPU count, you will see 8. If in your computer you have 4, what will happen is the result that you get here, it will be 2, because it will perform 4 on parallel and then perform other 4, and then finally doing that, doing the final result. All right, so the delay collection also has a nice syntax that you can use in your notebooks and in IPython, that is via a decorator. With, well, it is a decorator, but it's with using the @ magic. So you have, by using this, the @delay over a function, you transform this function into a delayed version of the function. So then you can use it directly and you don't need to do this. All right, so let's see how that works. Imagine we have a function that doubles the value of that function and of the argument of the function, and we decorate it here at the top with delay. So now if we run this, I have a delay version of this function, and when I call this function with an argument of, let's say, 4, we will see that this is a delay object. So as a quick exercise, and I'm like gonna give you like about 10 seconds or so, but we'll see it together. Try to modify the inc and add functions that we have at the beginning, copy and paste those functions, and then use this delay syntax to transform them into a delay version of the function. So if you are in Binder or following the material, you will have the solution right there. And you'll see that the only thing that we need to do is add in this delayed nice syntax over here. And voila, we already have delayed versions of our function. So we can use these functions. For example, there are multiple standard Python operations that are supported by the delay collection. So if we have the addition of 2 delay functions, then that will work just fine. So for example, here we have the inc version that we got over here. Did I run this? Yep. And then we are multiplying 2 and then adding to another 2. So let's see how that looks. In a graph, we'll see in a task graph, we see the 4 inks. There are 2 of these ones that have been multiplied. And then there are 2 of these multiplication results that are getting added. So if we compute this, we'll see it took us about 1 second. And the reason is also these multiplications and add functions are super fast. Like we are multiplying 2 numbers and adding 2 numbers. And that's why we just see this 0, 1. But in 1 second, we ran the 4 inks in parallel. All right, so we've learned more about what's Dask Delayed. I see there are a lot of questions on the chat. I sort of lost track. I'm pretty sure that they've been taken care of in the chat. If you need me to, this could be a good point to ask me a question before I continue. If not, I can continue, and then we'll get questions at the end. But as extra resources, if you want to learn more about delay, there is the delay lesson on the main Dask tutorial that is super useful. There's a PyData global tutorial that also have more examples on delay, and there are best practices and documentation plenty there. You can learn way more on there. So If there are not they're not big questions or something, or something that I should comment on, please let me know on the chat. If not, I will follow along with the next content, which is schedulers. It's a fun thing. All right. So remember that at the beginning, when we chat about having a task graph and then having a scheduler that will send the task graph to the workers, and then they will do the things in the workers. And the question is, do we have different kind of schedulers? And we mentioned single machine and distributed scheduler. So let's chat a little bit about what that is and how we can switch from one another and what we could do with one or the other. So far, we've seen the power of Dask Delayed, and we got familiarized with the idea of task graph, and we learned how this task graph needs to be executed to get the results. So we use the compute. And the one that takes care of this and managing all the stuff is the scheduler, I would say. So if you think of a task graph and then how it's tasks are sending and stuff, you can imagine sort of like this nice plot over here, and how things are moving along and what's waiting for one another, and then how things get computed. So far, we've been using what's called the single machine scheduler. So this scheduler requires like no setup. They only use Python standard library, and they provide a basic features on like local processes and thread pools. And now when I say these words, you might wonder, what are threads? What are processes? So here is a nice description. And by default, Dask will use the thread pool executor. So the thread is scheduler. It's the one that executes computations with this thread pool executor. And it's a default choice for Dask arrays, Dask DataFrames, and Dask Delayed. So far, we've been using, under the hood, this thread pool executor. If you use other collection, like Dask bags, for example, the default scheduler for that case will be the process pool execution. So we have this, the multi-processing scheduler that uses the process pool executor when we have Dask bag. And also you can set it up to be that in case you want. We'll see now in a little bit. And last but not least, there is a single threaded executor. And you might wonder, a single threaded scheduler. And you might wonder, like, well, why do we want to run things single threaded if the whole point of this is making things run in parallel? Well, when you need to debug, debugging in parallel can be very complicated. So in this case, you can set up your scheduler to be single threaded, and that will make your life easier when it comes to debug. So let's see a little bit how this schedulers perform in action and what it means when I use one or the other, and how the performance change accordingly to the case that we have. So far, we're coming back to our inc functions. So we import Dask, delayed. We have our delayed inc function over here. We use the nice syntax. And this was the example that we saw before, that we have inc over here. So we will use the inc version that is delayed, but we still need to decorate some this way. So we'll run this. And now let's switch the schedulers and see how long it takes for these computations to run, depending on the scheduler that we use. So as we mentioned before, by default, when we are using delayed objects, the thread pool, like executor, the threads scheduler is the one that is in place. So explicitly, if we set it, scheduler is equals thread, we should get the same result that we got before. So let's do this and check that we get right. We got the 1 second on the wall time over here. Now, one thing that we could do is modify how many workers we want to use. So for example, if I use the threads on the scheduler and I tell them to use only 4, we should get this to take 2 seconds. Because now instead of using the 8 that my machine has available, we are using only 4. So as you see, we get 2 seconds. So if we now try to use this scheduler the processes, we will get a different result. So let's check on this. Run this, and we got 6 seconds. Now we are using delayed, and it's recommended to use the thread pool executor, but we could still use processes. So this is what happened when you're using not the right scheduler for the right computations that you're running. If you were using Dask bags, it will be recommended to work with the processes instead of the thread. Now, you might notice that here the syntax is a little bit different. This is just another way of using to setting the scheduler. So what we're using it here is as a context manager. So we're saying with this scheduler, run things that are indented inside. You could still use it this way. But if you want to, let's say, only perform certain things with processes and then go back to the default, you will probably use the context managers. And then outside that context manager, you use a different one. This is an example of how to use the single threaded scheduler. We'll see that it takes 8 seconds. But not debugging things here. It's just to show you how you will set it up. And in general, these things are already set it. You don't need to change anything. You don't need to create multiple things with this stuff. We strongly recommend, actually, for people to use the distributed scheduler. And the reason why we'll recommend to use the distributed scheduler is because you will have nice visualization tools that you can exploit, and you can get performance reports, and you have more accessibility to multiple tools that you don't have with a single machine schedulers. Now, the distributed scheduler also works on your laptop. You don't need to have a cluster necessarily to use the distributed scheduler. But if you were to want to use a cluster, you will need to use a distributed scheduler. You can think of it as an advanced scheduler. It's like a scheduler that has a lot of perks that you can use and then check it out and get really interesting insights on the things that you're using. So one thing that it's interesting is, like, as I mentioned before, the distributed scheduler, it can run locally, but also can run on a cluster. You can use it on Coiled, for example, which is a cloud provider for Dask clusters, basically. And it will already provision a hosted Dask cluster for you. And you can try it for free. I will show you a little bit more how to use Coiled towards the end, and then how you can try for free towards the end. But for now, let's check on how can we create a distributed scheduler. And for this, we'll need to create first a client. So from Dask distributed, we'll import client. I am going to choose, in this case, 4 workers. And we see something interesting happening in here as I do 4 workers. So we get a client. You can inspect how your cluster or local cluster in this case looks like. You see here that we have a local cluster. So if I click on cluster info, you'll see I have 4 workers. And then I have total memory of 16 gigabytes. It says it's running. I do have 8 threads. And that's because I have like the possibility to have those in my machine. You might have only 4. If you are in Binder and you run this computation, you will see that you only have 4. You can check on the scheduler. You can keep clicking and then see up to their worker levels, and then you have some information on how many threads are on each worker and the memory for each worker. Now, how do we use this? When we create the distributed scheduler client, by default, it will register Dask a Dask scheduler. And from now on, when we do the dot compute, it will use the distributed scheduler. So for example, if now we do total compute, this will use a distributed scheduler. Now, one thing that I forgot to mention, and it's really interesting, is here you notice that we have this dashboard link, and it's a link that will send us to a dashboard. Actually, I will click on it and you'll see where we will have different things happening in here as we perform computations. One nice thing about being on using Jupyter Lab is that we do have on the left a Dask Lab extension where you can choose which one are the plots that you want to see. So let's check which ones do we want. So I will grab progress, so you can accommodate this one's. I will make it in a way that we can see the screen better. I want the task stream. I'll put it in here. I think I might be able. Oops. And then I want the workers memory. So we'll do that. And I will probably want the cluster memory, which should be here. This is sort of similar to, let me see, let's try to make, well, technically you usually can accommodate this to look one next to the other. I'm having some trouble in here. Let's close this and see if we can make this a little nicer. Let's close the cluster memory for now. That's kind of like a that. It's going to be a little tricky. I think it's because of the it's the size of the font probably. All right, let's try to put that in here. Let's do something like that. Let's see if we can work on that. Okay, back on. Let's see some action happening in here. So now if we do total compute, I should see something going on in this thing. Total memory size and CPU details. We do have many things in here in the task stream. We'll see some action now. So if I do this, okay, we see something happening. This might be too fast for this to register something, but let's see if, oops, we can get something going on in here. So you might notice that in the task stream now we have 1, 2, 3, 4, 5, 6, 7, 8. So one per thread. And these are the in computations that we perform. So they all run in parallel. And then you see here that there is a transfer. So they were transferred all. And at the end, we can zoom in on this. You have a tool over here to zoom in, zoom in, zoom in. And at the end over here, and it's too small, but this is a sum. So then we're summing things and then getting the output. So we'll restart this. Here that there are per worker, we have information about the memory. We have was managed and managed, spilled to this. For now, this is a little bit advanced and like manage and manage. I don't want you to worry about that, but we'll see more things happening in here as we go. If you want to read more about schedulers and how to do things with the schedulers and switching schedulers, there is plenty of information on the extra resources. And soon we'll have more documentation on the dashboard. But there are some links on how to read the dashboard, and hopefully we'll go over that today. So one thing I recommend is like whenever you're working between multiple notebooks and playing around with things, please close the client. So then otherwise you don't get warnings about being opening multiple clients and then having multiple computations going around. So I will close this one now on the schedulers, and let's move to something that might be more familiar to you all, that are data frames. Oops. And this will, okay, because this, I think this is getting low. Let's see if we can organize them in a better way. So the memory over here, we'll have the progress somehow there. I don't know why I can't put them all in a nice way. Okay, let's take a look at this. We have Dask DataFrames. So as we learned in delay, we can parallelize functions using Dask Delayed, but luckily we don't need to do the whole work to delay and parallelize all our pandas data frames. We have in Dask a collection that is a Dask DataFrames that has multiple of the functions and things that we use generally in pandas implemented to run in parallel. So we will use Dask DataFrames whenever we want to play around with something that looks like a data frame. So for most part, a Dask DataFrame feels like a pandas data frame. And the way that it works is if you can think of a Dask DataFrame as composed by many pandas data frames. Like if you see this image below, it might be a little, oops. I apologize for that. Might be a little small, but you can think of each of these pieces as a pandas data frame. So each of these pieces are called partitions, and each partition will be a pandas data frame. So we can sum them, we can perform operations, filter them, and do similar things that what we do when we have pandas. So let's try some things using Dask DataFrames and see what happened in using Dask. And one question that we had early on was, okay, when do we use Dask DataFrames, or when do we use Dask? So if you ever had something like a super big pandas data frame or multiple pandas data frames that you're trying to load all at once, and you might have seen this memory error message. So that is a great example on where you can use Dask, because Dask will take care of this and give things to the computation and then start sending the task as memory gets open, which in pandas you can't do. So during this tutorial, like the example New York City data set that we're going to use is not that big as Dask can handle, just for the purpose of time, but it could be even bigger and bigger, and this will work just fine. If you are working on Binder, you might see different results than what I have, because on Binder, we have even more restricted amount of resources. So we are loading on Binder only a smaller version of what I'm loading in here in my local machine. But let's see how this works. And as we go, you can have some more questions that we'll go over. So to start, we just prep some data. You should be able to run this. We'll get this data prepped. And the way that and now instead of having pandas data frames, we'll have Dask data frames, and we import this by doing the following line of code. So import Dask data frames as DD, and we're going to read a bunch of CSV files. So here in this, you notice this asterisk that we mentioned before. So I want you to take a look before we start to what this asterisk means and what are we doing when we read this files thing that we have. So if you check back in data, you'll see that inside New York City flights, we have 10 CSV files. So when we do dd read CSV files, we will be reading all of the CSV files at the same time. And each of these will be a partition. So let's read them. All right, so as we did before with delay, so far we haven't read everything. We don't have access. We have this sort of kind of structure of how things look like. And it's like similar to the graph and the things that we had before. And you have some information. You have like the columns over here, the data type, how many partitions, but so far we haven't done anything. And as you see on the right, there are not many things going on. And that's also because we haven't started the client yet. But we'll do that. So actually, before doing that, I forgot on cells. So let's do import from Dask.distributed import client. And then we'll do client equals client. Okay, we'll do that. So then when we do things on here, now we'll see some action on the right. So let's check the columns. So far, here we're not doing any compute, so we're not going to see much action here. But let's see how this data looks like before doing computations. So you can check the columns same way that you do in pandas, similar with the data types. And let's see. What is it? I'm seeing simple view simple. Okay. View simple. It seems like this will help. Well, that took rid of. I was just trying to find a simple way of seeing things better, but we'll stick for this for now. We'll figure it out for the next tutorial how to get things managed so you can all see better. We can get the partitions. So if we have 10 pandas CSV files that we were reading, then we will hopefully see 10. So if we run this, we'll see 10. And then we can still visualize. Like so far, the operation is the read CSV. So this is how it should look like. We have 10, and then we should get an output of each of this one if we read them. So far, we haven't done any compute. We haven't done anything yet. So not much of an action happening on the right. So remember, like in pandas, you can always take a sneak peek on how your data frame looks like. And here you can do too. So if we do head, you'll see there's something happening here. Like we have this read CSV and we have some, let's see, and then this is head. And what happens is that when we run or when we do the dot head, this is triggering a compute from a piece of the data frame. So then you can see the first 5 rows. And you see that while we're here, we have some action going on and we have different memories going on. The progress bar, things happen too fast. So that's why we're not seeing much action here, but hopefully we'll see in the next couple of computations. So this is what we did before. I forgot that I have it here, but well, we did it already. So we can actually start it even again. And it will, this is what happened when I wanted to show you what will happen if we start another client. And it will tell you, hey, I already have this thing going on. It's already in use another, but we have it there. All right, so if we keep going, one thing that it's interesting to mention is if we would like to perform some of these computations in pandas in all the files that we have, we will need to do a for loop where we will go over each of these files, reading all of these files and performing the computation that we want on these files. And that can take some time. We could use delay to optimize this, but in general, we don't need this because all of this is implemented in the Dask DataFrames collection. So let's see how we would compute the max of the column departure delay, the delay, on all of our files. And then let's see, what do we get? And it's the max overall. So this is how you would do in pandas. I mean, similar, same syntax. Now we're using a Dask data frame instead of a pandas data frame. So far we haven't computed anything. I want you to get an idea on visualizing how this thing will go. But this is a small figure and it's hard to read. But the important thing that is happening here is we have multiple calls that read each of the CSV files. You get which one you will get which one is the we'll do some computations and get the maximum of each of these ones, and then we will aggregate them all and then get the final and then know what's going on. So up to now, like up to this point, everything is what we call lazy, like nothing has happened. We have the graph set up, so then things will go, when we do compute, it will know what to do and it will give us the result. So if we do this, compute this, we'll get in some time, almost 2 seconds, a little bit less, what's the maximum of all these values. So all of these are pandas-like computation. So let's keep doing some of this so then you get an idea on how you will do other pandas-like computations in Dask. So I'm assuming this I don't know if these are running, but if we try, it might be that I trigger a different dashboard, so we can't see this, but I'll give it a try right now. So let's try to see, for example, the total of non-canceled flights taken. So notice that we have a column called cancel, and it's a Boolean. It's a true or false. So we do the non-cancel and we sum them. How we compute this, we'll get the total of these. And I'm not seeing actually here. So what I will do is I'm going to close this, guys. And for the sake of seeing things nicer, I'm going to get the dashboard on. So I think it will be a little bit easier to visualize. So, oops. All right, so we do have a dashboard here. Just gonna, for some reason, it's super small. Okay, so moving along. Over here, another example will be a group by operation. So let's say that we want to see the non-cancel flights taken by airport. So we'll see filter the non-cancel flights from the data frame, group by origin, and we want to count on the origin. So there are many computations happening here, but if we hit compute, you see some action happening in here. I will, for some reason, I will scroll to see this part for now. We are seeing the get item operation that you saw on this task graph over here. They're over here. We have some group by count chunks, and then we have some transfers. So you see all the tasks happening here. Now, if we do another kind of operation that you can do is computing what's the, here. What is the average departure delay from each airport? All right, so then we have origin. We know we're grouping by origin. Origin was each airport. And then we see the departure delay. We're grabbing that column, and then we're computing the mean. Let's see, what does that do? Then you see now a couple of things happening on this progress down here. As we compute, they kind of like disappear and get released, but then I will go over what is happening in here, that we have all the tasks of each type getting compute. And we'll see some things that take a little bit longer, so we can explore the dashboard soon. So we have another computation that you can do is what day of the week has the worst average departure delay. So then you don't want to fly on that day, probably. So then let's see what happens. So we group by day of the week, and then we take the mean and the index max for that. So we'll see 5. And as you see, things happen like super fast. And this is like, it has a good amount of data on it. I believe that we check over here. We might have checked the length of this. I didn't, but of this. I didn't, but I could actually, we could compute the length of this. Let's see. We can compute what's the length of our data frame. But if you see, we have like 2 million, a little bit more than 2.5 million rows, and things are happening quite fast. So now, one thing to keep in mind is like so far we've done multiple computations on this Dask data frame, but you might have noticed that every time we are reading this CSV, we are doing all this stuff. So if you are doing computations that share certain tasks, you might want to kind of coordinate those in a certain way to take less time. So let's see what I'm talking about. For example, let's see that if we want to compute the mean and the standard deviation for the departure delay of all non-canceled flights, since Dask operation are lazy, those values aren't final until we hit compute. So if there is a value that I will need in both of them, then we might want to generate sort of a recipe that I can use both of those. So for example, by doing things one at a time, so we have the non-cancel, and then I want the mean, and then I want the standard deviation. So here I'm doing this like twice. So if we time it, we'll see that to compute both of them, this takes about 3 seconds. Now, what happened if I actually pass this mean delay and standard delay to a Dask compute? In that case, it will use the non-cancel. It will have that in memory over there so that it should take less time. So we do import Dask, and then we will do it in this way. We will do a Dask compute of these two things that have the non-cancel part share. So do that. See multiple tasks happening, and we see that it took like 1.8. So it's almost like half the time. It's like about half the time from what we did before. And the reason is basically because we are reusing that thing that we have. So if you want to check the graph, the task graph, you can see it here. It's going to be a little bit complicated because it's small. I encourage you to go and look around, but you'll see that it's reusing these read CSVs that are under the hood over here. So I'm going to close the client up to this moment, and we will move to the last part where you can see Dask in action on machine learning, and hopefully we'll get to try Coiled too. So I'm going to close over that, and let's go to our last notebook. We're going to be doing some machine learning here. All right. So I think I want to see if, okay, this, let's see if we can get our our task stream going on again on a nice plot, and our progress. I want you to take a look at the progress part too now. And we'll do the other plots. You can read about the other plots and how we manage those things on the documentation. But these two are very interesting, and we'll see some things going on here now. So parallel and distributed machine learning. Okay, so this material has been based on the main Dask tutorial that it's very great. And actually, I would encourage you to follow up that. There's an extended version of this. And we don't want to reinvent the wheel, so we are reusing some of that material. Now, so far, we've seen how Dask makes data analysis using kind of Dask DataFrames and Dask Delayed, scalable. And now let's see how can we use Dask-ML, that's machine learning, to allow us to use more machine learning in parallel and then in distributed manner and hopefully get things faster. So in machine learning, we have, as we mentioned before, we still have similar problems than in general in our computation. We could have CPU-bound problems, which are compute-bound problems, or memory-bound problems. So CPU-bound problems are problems that fits in memory, but it just takes too long to compute because there are many combinations of things running. So for example, hyperparameter combinations or large ensembles of many models. So you're doing one thing over and over again, and that's why it's taking longer. And then we do have memory-bound problems where the data is bigger than RAM, and sampling isn't an option. You not necessarily always you can sample. So similar plot that we had before. If things fit in RAM, use Scikit-Learn. If things don't fit in RAM, let's start using Dask-ML and think about distributed computing. So when this condition are met, when you have things that are bigger and things are taking forever, then you might want to leverage the multiple machines usage. And you could use a cluster, or you can even in your machine try to use distributed computing to perform these computations. So overall, in general, if we have memories that fit in models that fit in memory, you will use just Scikit-Learn. If you have large models, we will encourage you to use the Dask-ML joblet and your favorite Scikit-Learn estimator. And we'll see some example of that. And for large data sets, you want to just use Dask-ML estimator, which are versions of these estimators that have been optimized to run like with large data sets. So quick overview over Scikit-Learn, so that we just get an idea if you're not necessarily familiarized with this. In general, whenever we want to train something, things to start off, you load some data, you import Scikit-Learn module for whatever machine learning algorithm you want to work with. You create an estimator for that algorithm, you fit your data, you fit it with your data or our data or the data you want to use, and you expect their own attributes, and then you check the accuracy on the model. And I just like super oversimplify how machine learning training works. Please no one get offended about this, but overall, this is the idea that we want to like go about and see how to optimize this. So in general, like Scikit-Learn like has a nice API, and things consist of you instantiate an estimator, for example, linear regression, random forest classifier, and then all of these models have hyperparameters that are passed to this estimator when it's created. And then you call estimator.fit on your data to train this estimator on the data you want to use to train. And you use this estimator to kind of like inspect attributes, make predictions, and so on and so forth. So here, X will be an array of what is called features. Is that what you're using to predict? And Y is an array of target variables. Is that what you're trying to predict? So some Scikit-Learn will do here. So far, we're not using Dask. Simple Scikit-Learn things. We want to make a classification. So we have some data. We get X and Y. And X here, like you have samples or features. And a feature is also called an attribute. It's something that you measure, a property or phenomenon that you're trying to analyze. So let's imagine that we're trying to predict the length of certain flower. And then maybe for that, we want to know, I don't know, what color the flower is, or the age of the flower, or how the size, the length, the width. Those could be, all of them could be features. And then Y is the target. So we were just saying that we wanted to predict, I forgot what already we wanted to predict, but let's say that we wanted to predict the color of the flower or something like that. That will be your Y target things. And they could be real numbers for regressions or integers for classification, could be multiple things. But in general, for this case, we have 4 different features, and those are the columns. And then each of the rows is a sample. And then Y should look something like, in this case, it's zeros and ones. So for example, is it blue could be the question, and then you have yeses and no. So it's zeros and ones. And if you want to, for example, train or fit a support vector classifier, we're not going to get into what this support vector classifier is. This is a simple example to show you how things work. If you want to read more about support vector classifier, there's a link over there that you can go and check it out. But as we mentioned before, we import the support vector classifier from somewhere in Scikit-Learn. We generate an estimator, and then we fit that estimator with our data. So far, nothing crazy has happened. We're still in Scikit-Learn world. We have the support vectors. We got that, and then we can score this estimator to see the accuracy. And we got a 0.9, which is a good thing. There are multiple approaches to score an estimator. You can read about them all. We don't want to get into the details of what's happening when we are scoring and how we're scoring, if it's good or bad. This is for the purpose of showing you how Scikit-Learn works. Now, imagine that we just fitted a model with just one parameter set. But now let's see what we would do if we want to explore multiple combination of parameters and see if we can get a better scoring, or we can train all these different combinations of models and see which one is better. So for that, we'll do a grid search. And so we imported that from Scikit-Learn. Now we have our estimator is still the support, the one that we have up here, the support vector classifier. And before we only use a random state 0. Now we're going to use gamma, random state, 0, probability, true, and then we will actually go over these other parameters. And we'll try all the combinations of this. So we want to do a grid search. If you see, it's like doing the same thing with multiple parameters a couple times. So we do a grid search fit, and still in Scikit-Learn world, we are having, as you see, 4 candidates, total of 8 fits, and it's doing some computations over here. So still all in the Scikit-Learn world. But as you notice, it's like we're doing the same thing multiple times. So this is a good candidate to use Dask, because all of this can be run in parallel. So here we got, and then after you do a grid search, you can get which one are the best parameters with the best score, and then you can train your model on that. So when you have a compute bound problem, like single machine parallelism with Joblit. So Joblit could be used, and we'll see how to use it with the Dask backend to run things in parallel. So here is sort of like an idea or a graph. It's not necessarily a Dask graph on how things could run in parallel for this classifier. So you have your training data, and then you have like all these different combinations and options of that you can pass to the model, and at the end you choose which one is the best. So if you ever use Scikit-Learn, you might have landed into this njobs keyword, and everyone tells you just put -1 and then it will do it in parallel. Well, what's happening is when you specify njobs equal -1, it means running the maximum possible of number of tasks in parallel. So you could do that. Actually, we'll do it right now. It's still on Scikit-Learn Learn. Let's actually set it over here. We'll do this on -1. And this is running in parallel using Scikit-Learn. So took 6 seconds, 7. So if you notice, before it took about 13, 14 seconds, so it's about in half the time. And that's a good thing. Now, if we want to run this in a multiple machine parallelism kind of thing, we could use Dask with joblib. So this will look, for example, research will look a little bit more like this. But in general, what is happening is we'll have our jobs being trained over like multiple machines. So luckily, the developers for both Scikit-Learn via joblib and Dask kind of like work together to make things kind of like collaborate and make it for you easier, so you don't have to modify your code too much. So if we want to do extensive research, it will take some time, but using Dask, we can run things much, much faster. So let's get our client going. So I'll have this, oops. Why is this telling me that something running that I didn't close? So you guys, you need to close your clients. We'll actually just, let's use this dashboard. Oops. If this happens to you, oops. Let's just get this on the task stream, so we coordinate that. All right, so now things are clean. You should not be seeing all these messages. I forgot to close a client, but let's move up. So now let's do this param grid by using the Dask parallel backend. So far we haven't touched anything. I'm going to set up things. I want to do a param grid search with all of those different combinations. So still have the n jobs -1. So far, haven't done anything, just set up this. And how do I tell joblib to use Dask? So the way that we do that is import joblib. All right. And we'll create like a context manager with joblib.parallel backend, and we'll tell it, hey, use Dask. And here you pass the data. And then we will do the grid search fit using Dask as a backend. So now we should see some action happening on the dashboard. So, all right. So one thing to note is that now you can see this task happening. Here are all the tasks on the bottom, on the progress. You have all the tasks that have been computed that are like the accumulation of all these tiny ones happening over here. So the colors, if you see in gray, so gray is like that are ready to go, but it have not been computing yet. When it's all full, is that they are released in memory. So we'll check that now again. But this took about 30 seconds. So as you notice, it's like things were made and easier that you only need to tell joblib to use Dask and things will run. So now we get that the best model is, in this case, after a run in 30 seconds, run multiple combinations, like 72 fits have done. So there was 36 combination. There was a cross validation of 2. So then we got 72 fits. And we got that the best parameters were the ones that we have here. So we use C10, kernel, RBF, shrink and true, and then you get a score of 0.908. Okay, so that's kind of like an example of a compute bound problem. Now, the memory bound problem is a different kind of problems that you can have where you can also use Dask. So what we do is let's create a problem that is a memory bound problem, and then let's see how can we use Dask to solve this. So here we will create some data some data with Scikit-Learn. So we make blobs, and we use the sample of 1,000 and then create some centers, and then we will expand this kind of cluster-like data to some more. So far, doing some centroids over here. And I will, if you are running on Binder, this is a warning. Oops, my machine is getting hit. Okay, if you're running on Binder, please modify this number to be something much smaller, like 15,000 or 10,000, because things can get bigger. I run, if you're not in Binder and your local machine and you want to try this out, you can make this as big as 200,000. If you got 16 gigs of memory, this will run and takes about 10 minutes. It will compute, but it takes about 10 minutes. And you need that much of a memory to make things work. Not it will run, but it will take like even much more long. For the sake of showing you right now, I am going to run this computation with just 60,000, but it can handle more. Where what we're doing is creating actually even bigger blobs, and then from those blobs we're like concatenating things, and we will train a k-means using Dask-ML. So far here, I've only created this array. As you see, it's not that much of a thing. We haven't done anything. And this is a good example, actually, where if you see that, oh, in my laptop things are not fitting, I need to go there, then you might want to try Coiled. We will try it now in a second and see how we can run actually much bigger things and get it to work. So let's try to train this k-means. So if you notice here, we are importing k-means now from Scikit-Learn, but from Dask-ML, because this is the one that is optimized and has all the things that we need to be able to run this in a distributed manner. So we got our model. Let's fit the model. And this will take probably about 2 minutes. And I want you to explore a little bit the dashboard here. So you might see that as we go, in the bottom part, we have this progress bar of some that have sort of like 3 colors. So we have in gray is the amount of tasks that are ready to go but are not running yet. So it says 500 out of something. Then you have a color bar, and you have the color that is solid, which means things are computed but are still in memory. And then the transparent ones, that is, things have been computed and have been released from memory, right? So soon we're going to write more documentation of this, and we will add it to this tutorial, and hopefully we'll do like a nice document to add to the Dask documentations. But so far, like you can see here, like the difference. And if you check on here, you can see here it says all 500 in memory 0, and they're ready to go for 199, but like they're not going yet. If you see this one, for example, it says all 500, and then if you see in memory there are 430, but now things move. Let's try another one, like this one. And then it will tell you how many are in memory, and then how many are not in memory and then ready to go. And this is a nice visualization and things you can do. And over here, you see all the tasks like getting compute and then going and on over there. And then if you want to save all what has happened in the task stream, you can create what's called a performance report. You can Google, like in the documentation, Dask performance reports, and then you'll see how to get all this information. I will see, can I put let's check the memory since we have it. We're right here, workers memory. So you'll see let's put it right here on the side, just to learn a little bit about this memory. You see that it's processing, every worker is doing something, and you have the managed memory, unmanaged, and then so far we haven't needed to spill to this because this actually fits in memory. So things should be fairly fairly nice. Okay, this should be finishing soon. It's taking a little bit longer than I expected. I think it's about to wrap up. Yeah. Right. So yeah, we have the sum. So we're kind of like getting to the last part. These ones you can always stop them if you like to inspect them and then go check it out and then see, okay, what is this one? And this one should be yellow. So yellow, the color matches with what is on the progress bar. All right, so we compute this, took 3 minutes, that 2, maybe something going on, but we got that. So now if I want to run this faster, we can check this and then close, but this is when I would suggest everyone to try Coil and see how we can make this better. So for now, I'm going to close this. Now, Coil allows you to try to get your own big cluster in the cloud in super simple way. So you import Coil, and then you will create. I already have an account. If you want to try Coil, you can create an account. Up to this, I'm going to start creating a cluster, but so you can see how things work. This is actually cloud.coil. So, oops, we're going to go here. So up to currently at the moment, signups are blocked, but starting to now you can sign up. Signing up is for free. And if you want to try the free tier, you need to send an email to support@coil.io. We will send you, I'm going to start to create a cluster in here, but you need to, what's it called? You can send an email. And the reason why now we're asking you to send an email to support@coil.io is because we've been having some Bitcoin miners attacks. So then we want to control that not anyone can basically overuse or abuse our free tier that we want for nice people like you try it out. So if you want to try Coil and get your cluster and then play around and see and run the same tutorial, we will we'll ask you to send an email and then say that you attended the tutorial and you want to try Coil for free. So to spin up a cluster, this is what is happening here. You can see on the right that it's trying to get some workers. So far has done it. It takes a couple of minutes. You will need to provide a software environment. In my case, I created a software environment for this case. You can actually use this same one software environment if you're interested in running the computations over here. Just to let you know, there's plenty of documentations about creating your software environment, you run your things. But as you might notice, I'm still running things on my laptop, and then it will be computed on the cloud. So hopefully in 1 minute, we will get our cluster up, and we'll start seeing that over here, we are getting some workers going. So far, this is giving us some information about what kind of machines are we getting, and so on and so forth. But yeah, so once we have that, I can run the same computation. You can see the dashboard too, and you will notice that things will run much faster. Right, this is taking some time, but here you'll see also some interesting things. Okay, it's telling me, okay, it's giving me the workers. There we go. You see 3 out of 10. Takes a little bit of time till all of them kick in. And once we have that, we actually can see the way that we create now our cluster is we do client equal, and then to the client that before we didn't pass anything, now we pass this cluster that we just created in Coil. So let's see how we do that. And now we got a different address for the dashboard. So so far we haven't gotten all the workers yet, but I will click on here so you can see. that we got, what, 5, 6 so far. It's getting some time to provide me the rest of the, oops, but for some reason, it is stopped at 6. Okay, let's try it out with a couple more workers than the ones that I had before. Let's see. Right, so we got our cluster over here, and then cluster info. You see now we have way more memory compared to what we had before. And we can run now, if the same example, now we run it, but using 200,000 samples instead of using just the 60,000, this should run in a good amount of time, considering that we got a bigger cluster. So we'll just do that. In this case, we have a good amount of memory, so then we can persist the data so the rate that we created it. I will ask you just to go to documentation and then check this out, but this will make our things go easier. And because we have the memory, we can run this. So far it's persisting that data, but I can keep doing things because it's happened on the back. And let's try to train this bad boy. All right, so if we're gonna time this. Hopefully things are happening. All right, so we'll see on the dashboard. I'm just gonna move up the dashboard here so then you can see what's going on. Oops, might have close that. Things are happening. Oops, maybe. Oh, it's giving me more. It's giving me more workers, and then that is actually causing. Okay, let's just for a moment we would do actually. Let's run that again. Now that we have all the workers. Let's do this. Let's close the client so we can clean this up, and then let's just run this competition again so then you can see how this runs. So we got that. This is the right cluster. Oops. All right, so let's run this. All right, there we go. And then we're going to try to fit this stuff. Oops. Let's pause. Okay, this is training. It's getting, something is happening here. It's one of the workers that seems to be stopped. I think maybe something happened in the dashboard. 3, 4, 5, 6, 7, 8, 9, 10. Something happened that, but things are computing. I wonder if there was an update on Dask-ML or something like that that actually triggered this to not be computed. But as an example, I could tell you that when we were running this, things were running like in 30 seconds with 4 times the data we had before. So we can check, actually, things technically are running. So Coiled has some logs that we can see and see if there is something happening in here. Okay, some workers, get data. Okay, so it seems that maybe something happened on, I tried this earlier and things were working, but it might have happened that something with the connections is not working. See, That's the nice thing about Coiled. You can get to see the logs and see what's happening. Let's see if this kick in. Seems like something got stuck. So I wonder if this might be, I want to try one more thing because I think another worker came up when this was on. So let's try this one more time. And see, actually, kernel. I cannot even close this. So, okay, kernel, let's see, stop. Let's see something quick. Just going to, actually, we don't want to restart this, but we do want to get that cluster up. And let's see if we can, because this is running, but the problem seems to be with the fit. So we're gonna try this one more and see what happens. All right, okay, things are moving now. I think it was just what happened was in the middle of this competition, one of the workers show up and it was still pending and I didn't wait for that worker. So then I mess up, I apologize for that. Things are working and are running. Now we see in the dashboard, we got all the things. This here, you got all the tasks that are processing and you get to see the memory. If you would like to see another kind of dashboard things, this is another plot that is interesting where you have, it's like the task graph and how things, these are many tasks, so it's a little bit hard to see, but you can check that. Another interesting visualization you can check is the groups, where you get to see by group of tasks how things are getting computed. So now we're doing like a get item, and then how things move on and the progress more of on a task. But hey, there we go. Look at, we got the status, back to the status page. You see this took 1 minute compared to 3, but we're doing 3 to 4 times the data. So it's much, much faster because now we have a powerful machine and we have all the memory that we can use. So you can still compute the labels and then check what the result was. But yeah, that's like a nice show off of what you can do with a powerful machine and how easy you can request a big cluster with using Coiled. So if you want to try Dask, if you want to get more into Dask and learning more, there's plenty of documentation, as well as there is we can put on the chat too. There are Dask trainings by Coiled that are like 4 days that you can do. So that's a nice it's a nice thing that you can do if you want. We will send out after the tutorial, like we will send out the information on how you can request your free tier on Coiled. So feel free to ping us back, and then you can join the Coiled Slack channel if you want to try Coiled and then learn more about Coiled. And if you want to learn more about Dask, we'll welcome you to try the Dask discourse and then also the Dask Slack channel, so then you can check all that. I know that this has been a little bit longer than what we expected. I apologize for having to troubleshoot some things live. If you have any more questions, things you want to try, let us know. You can always also ping us on Twitter or anywhere. We're happy to get you on board with Dask. And of course, if you want to try Coiled, happy to do that too. So that's how it goes. So, oops. Dashboard not connected. All right. If we don't have any more questions and stuff, I will suggest you, keep following us on Twitter and Slack and any place that you want. And this will be published soon, probably on YouTube. So, thank you all for staying put and for hanging in there. I know it was a little bit long, but yeah, it was just great to have you. And now we'll end up the stream right now. See you. Hope you have a great night, day, or whatever it is like you were following, or where you're following from. Goodbye.